In this activity, we're taking a look at how our notions of sensitivity can be applied to an example system. So in this case, we're interested in quantifying the sensitivity of the closed loop transfer function. So again, that's that t that we had in the previous slides, and how that changes with a parameter in our transfer function for our system, capital A. And so before we had this sensitivity function that was a function of g and a delta g. In this case, we can get a little bit more specific and we can kind of talk about the changes in A. So you can kind of think about a delta A as a function of A. Instead of delta g as a function of g, you can still do that. But then what would be required would be to say, how does then G change with A? So there would be a second relationship. So instead, it's a little bit more direct to just think about, instead of changes in the model as in its entirety from the perspective of just the transfer function G, now we can think about specifically if we think that only A is changing, then we can directly assess the sensitivity with respect to A. So give this a try, and then I'll go through my solution. All right, so the transfer function that we care about is the closed loop transfer function. So that's t, which is, in this case, there is no controller k here. There's nothing there, or it's just unit, and there's also just unit feedback. So that means that our closed loop transfer function simplifies down to just g of s over 1 plus g of s. We plug in what g is, then we get to here. And then we multiply top and bottom by this s times s plus alpha, which yields the closed loop transfer function that looks like this. And so now the sensitivity that we're interested in getting is the sensitivity with respect to A now. And so just like I was trying to motivate in essentially the tee up for this activity, the fact that we're interested in how does the closed loop transfer function change with respect to its nominal value to changes in A compared to its nominal value. And so, so notice that essentially we've replaced G here with A in the previous identity, and that's because A is the thing that's actually changing. So it's a piece of the transfer function G. And so when we do the simplification, now we get down to this point where again, A and G have been kind of interchanged. And so we go ahead and put A here, and we put T down here, and then we take the derivative of T with respect to A, which is like this, which again is given by that quotient rule, and gives us this value. Again, when the dust settles after you've cleared some terms, you get down to a term that looks like this. And so that sensitivity function is indeed essentially given if this changes, how does the performance of Y tracking R, how is that changed? And so this is the value that does that. And so an interesting thing is to note that, of course, this is also a function of the value of S. So much like our discussion of the fact that S plus T is equal to 1, some tricks can be done in order to essentially change how S and T, the magnitude, say, of S and T, depending on the frequency, little s. The same thing is true here. And so that sensitivity is a function of the frequency or Laplace variable S. So that's an interesting thing to keep in mind, and something that then affects that depending, so that your sensitivity can be different depending on different frequency values. And so that could be an important factor depending on what your reference looks like and what kind of noises you want to get rid of, and to know how that performs at the different frequencies will actually tell you what happens in practice.